positive nuclei. I'm using plural here because whenever you form a bond, there must be two atoms. You can't form a bond if you are by yourself. This is why I'm using the plural form of nucleus, nuclei here. Okay, so this has to be plural. Okay, positive nuclei. You need two atoms to form a bond. A single atom can't form a bond. You can't marry yourself. You can only marry somebody else. Okay, so that's what a bond is. So we also have a new type of attraction that I haven't told you before, but put this down now. These two molecules, they may look like they don't connect in any way. Actually, they will attract one another weakly by a type of force known as weak van der Waals force. Okay, I believe this guy is Russian. Okay, they hold a strange name. So van der Waals is the name of a guy. Okay, and the name of this force is called van der Waals force. Okay, because he discovered it. Okay, these molecules, they are attracted to one another by these very weak forces, which is why it's very easy to separate them. It doesn't take much effort to separate these two H2 molecules. And as a result of that, as you'll see later in the notes, we'll go through each and every of the structures, don't worry. They have very low melting and boiling point, this one. So this is what a covalent bond is. So this is what a covalent bond is. So a bond, is a type of attraction. So this attraction holds the two atoms together, so that's covalent bond. So you may highlight that in green. What about ionic bond? Yeah, there is metal and non-metal. Do you remember the name of those two ions found in ionic bond? What do you call positively charged ion? Cation. What about the other type of ion? Anion. So I want you to draw a lot of positive, negatively charged ions in here. What do we call? So individually these are called anion and cation respectively. What about the entire structure? There's an L word that we use a lattice. Okay, so the whole thing. Can you draw the dotted line? Can use more colors. If you draw it very black, must be easy. Even yourself don't want to read it. Okay, so just use some colors here. So you have ionic lattice. Remember the word lattice, very important word. It means it is a very regular arrangement. So when you say ionic lattice, we mean this regular arrangement, okay, it is made of ions. The two types of ions being cations and anions. So where is the so-called ionic bond? Ionic bond is an attraction. And because of opposite charges attract, so you can use another color. If you ran out of color, it's okay, just use highlighting now. These ions, they attract one another by the so-called strong ionic bonds. So you see it here, and everywhere, basically, inside the ionic lattice. The ions, they're bound tightly by these strong green forces, known as the ionic bonds. So just draw this in the middle cell. And for metallic bonds, what kind of ions do metals form? Do they form positive ion or do they form negative ions? Metals. Metals actually form positive ions only. Why is that? Usually metals, they are found in group 1, 2, and 3. What are the charges of elements from group 1, 2, and 3 when they form ions? It's positive. Positive 1, positive 2. You can refer back to this part. Where are the metals on the periodic table? They are found usually in group 1, group 2, and group 3. And because of their position, they form cations of +1, +2, and +3. Does the table ring a bell? Yes. Does the table ring a bell? If not, do revision. Okay, yeah, so it's many pages back. Okay. So metals only form positive ions, which is why in this structure I want you to just draw positive ions. Don't draw any negative ions for metallic bonds. But then, in between these ions, you draw some electrons. So these electrons, it acts as glue. It acts as glue, okay, to stick the metallic ion to the electrons, okay, holding the structure together. What happens if I take out the electrons? When I take out the electrons, what kind of ions do you see in this structure? take out the electrons. If I take out all the red electrons, you see only positive ions. And light charge ion, what do you remember what happens to them? Do they attract or do they repel when they have light charge? Light charges will repel. So you can say thanks to the electrons, these ions they do not fall apart. Okay, the structure does not fall apart. Were it not for the electrons, the structure will fall apart. Okay, so the electrons hold the ions in position. So these attraction, we call this metallic bond. Okay, so you can draw a connection between like these positive partner and negative partner. We call this metallic bond. Just remember that when you use the word bond, it means some kind of attraction. And a bond has to involve something positive and something negative. Okay? So put this on your worksheet first. Okay, yeah, I want you to do this do revision using the summary. So and once you're done, you can put down a bond is an electrostatic attraction between something positive and something negative. Which is why you see I only drew something in color green when I have a positive and a negative charge particle. So you see a green line is drawn between any pair of positive and negative charge particles. So this is positive, this is negative, so there's a bond. Positive and negative, so there's a bond. Positive and negative, so there is a bond. So there is a bond whenever there is something positive and something negative inside these structures. So at least there is something in common between these three types of bonds. And this is that they all have something positive and negative. Okay, so learn this new word if you haven't already. Electrostatic attraction. Electrostatic attraction means the attraction between something positive and negative. Okay? So something positive and negative. And once this is like once you copy this, okay, we can move on to the bottom of the page. So you see I already completed this table for you. Nothing to fill in here. Nothing to fill in the top table. But after you are done copying this into the middle table, I want you to focus on the bottom part of the same page. Ionic bonding. Okay. So I already made a summary for all of you. Okay. So just know that ionic bond, the structures, they are called giant ionic structures. Do you remember how we determine the ratio of ions? What is the formula of the compound formed by sodium and chlorine? Yes, what is it? Sodium and chlorine, what is the formula of the compound? Is it Na1Cl1 or Na1Cl2 or Na2Cl1? Na1Cl1, yes. Okay, so can you put down giant? You see, I put some indentation here. Yeah, this is because under each type of bonding, especially covalent bond, you see there are two structures that are classified under covalent bond, which is why on the next page, yeah, you can see that I made the title here, a covalent bond. But then under covalent bond, you see there is an indentation because simple molecular structure is a subtype of covalent bonded structure. The other type of covalent bonded structure are simple molecules. Okay, so simple molecules and giant covalent structures, they are both subtypes of covalent bonding, which is why you get indentation there. So can you put this in the blank space below? So ionic bonding. So under ionic bonding, we have giant ionic structures. And different compounds, they contain ions of different ratios. When you have NaCl, what is the ratio of Na plus and Cl minus ion? Is 1 to 1. Yes, 1 to 1. So can you put down Na plus to Cl minus equals 1 to 1? This is what the number suggests. But then when you have other formula, so let me check if you have done revision. Okay, you can take out your periodic table if you like. Can you tell me what's the formula formed by, what is the formula of the ionic compound formed by magnesium and chlorine? Magnesium is from group 2. Fluorine is from group 7. What is the charge?
Mg3F2.
It's actually just
3, 2.
MgF2. MgF2. Yeah, why is it MgF2? Because Mg is from group 2, which means it has 2 plus charge. F is from group 7. What is the charge of something from group 7? -1. Remember crisscross group? Okay. So, right. So you can swap the numbers around, and then you have Mg1F2. So similarly, when you do this to Na and Cl, you know Na is from group 1, Cl is from group 7. So this means they have charges of 1 plus and 1 minus, respectively. When you swap the numbers, you get Na1Cl1. Yeah, the formula, you need to know how to work it out. This is the most important skill in this chapter. So what is the ratio of Mg2 plus to F minus ions? Is it 1 to 2 or 2 to 1, as suggested by the numbers in here? 1 to 2. Okay, don't forget the number, you can really swap it, you cannot. Okay, you have to write the number in the same order they appear in the formula. Okay, so 1 to 2. Write down what this number is, represent. This represents the ratio of ions. Okay, so the ratio of ions. Right. And can you draw a diagram of the lattice? Underline the word 3D lattice. Underline the word 3D lattice in here, and then draw the lattice on the side. Okay, on the side. Don't draw it at the bottom. You see some blank space to your right hand side here. Okay, so draw this lattice for me here. So every ion is surrounded by ions of oppositely charged. Okay, so if you think of the positive ions as like boys, yeah, each of the like a boy, like a participant here is surrounded by like a girl participant. Okay, they are always like put in this alternating manner. So we call this a lattice. So after you underline the word lattice, just draw this diagram on the right. That describes a lattice. Okay, and you see, I wrote down each ion is surrounded by oppositely charged ions. Okay, and that they are present in ratio as predicted by the formula. So just copy the two formula on the side as well. If you have NaCl, then the Na plus and the Cl minus ion in this lattice, they will be in a 1-to-1 ratio. If you have MgF2, yeah, if you have MgF2, so if you have MgF2, the Mg2 plus and F minus will be in a 1-to-2 ratio, which means which ion must be present in greater number. When you see these two ions in 1-to-2 ratio, what does it suggest? Which ion has a greater number? 1 to 2 means for every one Mg2 plus, you will have 2 F minus. So F minus, okay? Yeah, so can you write down the number of Na plus ion is equal to the number of Cl minus ion on the left. But when it comes to MgF2, it's not the same. We say the number of Mg2 plus ion, when you double that, that would be equal to the number of F minus ion. This means the number of F minus ions is greater, because only when you double the number of Mg2 plus ions do you get the number of F minus. So for example, if you have 2, if you put 2 into this term in here, you get 4 for the red term. Yeah, that means for every 2 Mg2 plus, you get 4 F minus. You can put any number you like here. You can put 3. If you put 2 times 3, it will give 6. That means for every 3 Mg2 plus, you get 6 F minus. Yeah, you need to make sense of this ratio. Okay, you need to be able to make sense of this ratio. Don't interpret it in the wrong way. Now, we see some properties. Okay, so don't use the blank space below yet. Okay, we're going to use this now. Okay, the blank space below, we're going to write some notes. Okay, if you already wrote something there, write the thing I'm going to write in the notebook there. What are some properties of giant ionic structures. Okay, so we'll put this on the side. The first property is the high melting and boiling point. We can explain all these properties. Right, so high melting and boiling point. So the high melting and boiling point is due to the many strong ionic bonds. So there are many, you may want to use the space maybe you want to put this on your notebook. Okay, sorry. So put this on your notebook. And later you can draw a diagram on the worksheet. Okay. So there are many strong ionic bonds holding holding the cations and anions together. So holding the cations and anions together. That will mean it takes a lot of effort to separate them. So you can draw this. So draw these positive ion and negative ion in here. In order to melt something, we need to separate the ions from one another. For example, if you want to melt this structure, you want to move one of the ions away from the rest, right? So you want to move this positive ion away. What does it take to move this positive ion away from the rest of the partner here? You need to break some bonds, okay? These two bonds, they will have to be broken if they are now bonds. Okay, they have to be broken. But because these bonds are very strong, okay, it takes a lot of heat to do this. Okay, it takes a lot of heat to do this. So you can see we are focusing on just this corner, positive ion here. So you can write down these are strong ionic bond. To melt the structure, we need to use a lot of energy, okay, to break these strong ionic bonds. So strong ionic bonds requires a lot of heat to break. So requires a lot of heat to break because they are strong. This is why they have high melting and boiling point. Okay, so they have high melting and boiling point. So first property, explain. Okay. What about the second property? Why are they hard but brittle? Okay. Well, first of all, a lot of students think that when something is hard, they must not break easily. Actually, diamond is the hardest substance, the hardest naturally occurring substance, but it breaks easily. When you hammer diamond, you can easily chip it. Okay, so hardness and brittleness, they usually come together. Okay, so don't think that a hard substance must never break. Okay, it will break. Okay, so the second feature that I want you to take note of is that they are hard but brittle. Okay, so they are. First, let's explain why they are hard. So they are hard because they have many strong ionic bonds again. So if these bonds require a lot of energy to break, it means it's not easy to deform the structure, okay, to break the structure, okay. So you can write down reason number one. It's hard because of the many, again, strong ionic bonds. So these strong ionic bonds, they are like ropes, okay, that hold the ions in place. It doesn't allow any shift in their position. This is why it's hard. Okay, when you say something is hard, it means it doesn't change shape easily. Okay, and it doesn't change shape easily because of these strong break forces. Okay, what about brittleness? So brittle because when a force is applied, don't spell because like this, I'm just lazy. Okay, so you have to spell it properly. Okay, so because when a force is applied, so this we went through briefly, but we ended the lesson in a rush yesterday. So let me explain it more clearly this time. So you can draw two layers of ions. So just draw two layers. You can draw any layers, any number of layers you like, but it won't matter. Just draw these two layers first. When I apply a force, so applying a force will shift one layer off to the side. And what happens eventually is that you are turning attraction that we described yesterday. So these are attraction, you see. Okay, put a key on the side. This means attraction. The green line means attraction. Turns it into repulsion. Okay, so you see light charges repel. So this means repulsion. And eventually the whole structure will just fall apart. Okay, so the whole structure will want to move away from one another. So this is why it is brittle. You know, brittle things shatter easily, right? So once things shatters, they never go back together in one piece. And this is why. Once you have two light charge layers sitting next to one another, they will just fall apart. They don't come back together. Okay? So do you know why we say it is brittle? Okay, put down 3 points in here for me, please. So number one, at first, opposite charge partners are next to one another. So at first, opposite ions are next to each other. What is happening in the second diagram here? When a force is applied, okay, so you see you give it a nudge, okay, slightly. So this is a force. So when a force is applied, it will shift the ion slightly, okay? So the layer of ions shifts slightly when a force is applied. So what is point number 3 then? Point number 3 is that repulsion arises. Okay, so repulsion arises and this shatters the structure. So this shatters the structure. So try this tonight. I think I told you this yesterday. Just put a soft grain in your hand. Try to press on it really hard. You'll be able to feel that it breaks in between your fingers. Okay, this shows that it is brittle. Yeah, salt is actually pretty brittle. Okay? So you see that it is hard but brittle. The second property. The third property is that they are insoluble in organic solvents. Okay, but they are soluble in water. Okay, so water, can you put another term next to water? Water we also call aqueous solvent. So do you know what aqueous means? Okay, I think the word aqua means water in French. Yeah. Okay, so some of you don't know you have. Okay, so you know French better than I do. Okay, so aqua means water, and water is an aqueous solvent as a result of that. So it contains water. Okay, it contains water. So water is an aqueous solvent. So just know that they are insoluble in organic solvent, such as oil. Okay, such as hexane. Okay, so write down some example of solvents here. So solvents, there are 2 types. Okay, so solvent types. We have what we call organic solvent. So organic solvent are oil-like. Okay, so organic solvent. And then we have the other type of solvent, aqueous solvent. So aqueous solvent, the most important example will be water. Organic solvent, an example will be hexane. You can think of hexane as like oil. Okay, it's kind of like oil. Okay. So normally when things dissolve well in water, they don't dissolve well in oil. So things, they usually are soluble only in one type of solvent but not the other. Say for example, let's say in visual arts lesson, you use the watercolor to paint, right? Watercolor, they dissolve pretty well in water, which is why we call them watercolor. Yeah, they do not dissolve so well in oil though, okay? So in contrast, when you want to remove ketchup stain from your shirt, water might not do a very good job, okay? Because ketchup stain contains substances that are not soluble in water. But then, if you send your shirt with ketchup stain for dry cleaning, you know what do they use in dry cleaning? They are actually using organic solvent. They do not use water to clean your shirt or clothes when you send clothes to dry cleaning. And because it's more expensive, we don't normally send clothes to dry cleaning unless you really have something that cannot be removed by washing it with water. So these 2 solvents, they are different. Okay, yeah. So, and for different substances, you see, giant ionic structure, they dissolve well only in aqueous solvent. They do not dissolve in organic solvent. So can you put down what happens when you add salt into water? So this is what salts look like before you add it into water. It has this ionic lattice. As soon as you add it into water, so you add it to water, so add to water. Water has the ability to split, okay, the ions apart. So you will now have a bunch of freely moving ions when you add water. So the explanation, I think, is too difficult to explain to you at this point. Okay, so just know that when you add water, all the ionic bonds are broken. Okay, so these are ionic bonds in green. So the ionic bonds are broken, and you will end up getting a bunch of free moving ions. So what do we call this structure on the left again? Ionic lattice. So what do we call the ions that have very great degree of freedom now on the right? We call them mobile ions. Mobile because they can move around freely. They are not limited to one position anymore. Okay, you see here, you can't use the word mobile to describe these ions. They are fixed in position. They can't move. But once you add water to them, you free them. Okay, the ions now have very great degree of freedom. They can move around, okay, freely. So to emphasize that they can now move, we use the word mobile. Okay, yeah. So don't invent your own term. Okay, don't say free ions or something like that. We say mobile ions. Okay. Now, this is why they are not conductor in solid state. In the solid state, so can you put down solid in here? So this is in solid state. The ions cannot move. What is it? Can be what? The fan. Cannot move. And in aqueous state, we say, when things dissolve in water, remember we say it is in aqueous state. Okay? So in aqueous state means, when something is in aqueous state, it means it is dissolved in water. Okay? So it means it is dissolved in water. And when it is dissolved in water, the ions can move freely. Okay, and this is why they are conductor. Okay, so let me draw you another diagram on the next page, and you should also add on the notebook. Okay, to explain why they are conductor in the aqueous state. But on this page, any question first? No. Okay, so let's move on to the next page. We can in fact do an experiment to study the conductivity of substance. So studying the conductivity. You see that I wrote non-conductor in solid state. How can we be so sure that they are not conductor in solid state, but then how are they good conductor in aqueous and molten state? Okay, so the term molten should be new to you. Molten means something is heated so strongly that it melts into a liquid. An example of a molten substance is lava. Yeah, you know what is lava really? It's molten rock. You know it's rock, right? Lava. It's just that it is heated to such a high temperature that it melts to form a liquid. Okay, but when it cools, it forms a solid rock. Okay, so the term molten and aqueous I'll discuss in detail here. So studying the conductivity of ionic compounds. So, right. So first of all, we have this ionic solid in here. So salt. So salt or table salt is an ionic solid. We write the formula as NaCl bracket S. Okay. So table salt in the solid state equation as NaCl bracket S. Okay? So we don't want to write this like a term in here, table solid, it's too long. We'll just write NaCl bracket S. Bracket S means solid. So table salt is represented by this formula, NaCl. So in table salt, when we put it into a setup that looks like this, so in the lab we can set up this setup to study the conductivity of substance. So I hope you remember that the shorter arm represents negative terminal of the battery. The longer arm represents the positive terminal of the battery. So when we connect the setup through a light bulb, okay, so this is how we draw a light bulb. So this is a light bulb, and can you copy this one? You haven't been copying forever. Yes. Okay. So this is a battery. Right. So we have a battery. We are connecting the battery through a light bulb. Okay. Into the substance we want to test. So let's say I want to know if this sample of table salt conducts electricity. What do? I put a container here and I just pour the salt over. And if this is conductive, let me tell you what will happen. The light bulb will light up. The light bulb will light up if the substance you put in this container, okay, conducts electricity, because it completes the circuit. So currently, can you tell me if this circuit is completed or not? Before I put anything in that container, it's not complete, right? So you can draw a line here on the side to show that it is broken in here. Okay, so this is an incomplete circuit. Okay, so this is why the light bulb shouldn't light up. However, when you put a conductive substance in here, so let me put down if this is an insulator compared to when this is a conductor. So this way of testing conductivity is very straightforward. It is based on a very simple physics principle. And it is that if you have a conductor in here, it completes the circuit so that it forms a closed loop. And then electricity will start flowing through the circuit and the light bulb will glow. Okay, if you put a conductor in here, you see a closed loop circuit. It's a closed circuit, we say. So this is a closed circuit. Yeah, I'm not teaching you physics, but I believe this you have learned in science. Okay, so this will light up. But then, if you put an insulator means it does not conduct electricity. So there will be a broken circuit you see here. So this is not connected end to end. You see it's broken in here. So this is an open circuit, we say, or you can call it broken circuit. So broken or open circuit. In this case, the light bulb will not light up. Okay, so it will not light up. And that's it. So does not light up. This is a simple test, okay, of the conductivity of substance. And let me tell you, when we put table salt in the solid state in here, or we put this thing in here, it does not light up, the light bulb. However, when I do something to salt, so I can do two things to salt. Number one is that I put it in, have you all used this container in the lab before? Or have you heard of the name of this container? When we want to heat something very, very strongly in the lab, should we use a beaker? No. Why?
Because it's glass.
Because it's glass, and glass can melt. Okay? So we will use a container called a crucible. So crucible is a heat-resistant ceramic container. Yeah, so heat-resistant, but it breaks easily, so don't drop it, okay, when you use it. So ceramic container. Well, even beaker will break, okay, so you should treat all equipment carefully. So this is crucible. When you put the salt, which is still in a solid state, in the crucible, and then you heat it up very, very strongly using the Bunsen burner. So this is what will happen next. Okay, it will melt into a glowing liquid. Okay, so it will melt into a glowing liquid. So now it will look like this if you heat it to a really, really high temperature. Okay, this will now be called NaClL. We say that this is solid sodium chloride on the left, and this is molten. Okay? Molten means something is heated so strongly that it melts into a liquid. Okay, so when you apply heat using the Bunsen burner, this is what will happen. Okay, so right now, eventually you get this. Okay, so and write down the description of what molten means. So molten means something is heated so strongly that it becomes melted into a liquid. Okay, that it becomes. It should be noted that you don't use the word molten to describe water. Why don't you use the word molten to describe water? Because when something is already in the liquid state at room temperature, even without you heating it, the word liquid would do. But when something only exists as liquid, when you heat it, it will solidify. When you remove the heat, we'll use the word molten to describe it. Do you see the subtle difference between the term molten and liquid? So water is a liquid. We don't have to say molten liquid because it stays a liquid even whether or not you heat it. But lava is a molten liquid because it will only exist as a liquid when you heat it. Removing it from it will immediately result in it solidifying back into solid. Know the difference? Okay? Okay, great. So, means something is heated so strongly that it becomes melted into a liquid. So, put down just one example. Yeah, we say molten lava. So, the term molten lava is correct. But we don't say something like molten water. So, this is nonsense, okay? So, molten water, this is not true. So, what do we replace it to? We say liquid water. Okay? So liquid means something exists as a liquid. So mercury is a liquid. You don't say molten mercury either. Because at room temperature, even without heating, it exists as a liquid, right? Okay? So liquid means something exists as a liquid even without heating. So yeah, with or without heating. So with or without heating. But molten means it will only exist as a liquid when it is heated, and it will return to a solid when it cools. So molten means it will exist as liquid only when heated, but it will solidify when it cools. So when it cools. Okay? Yeah, so copy this first. Okay? Because we will see the word molten and aqueous a lot, okay, in the later part of chemistry. I need to get this concept straight. Okay? So what next then? Okay, when we put this molten NaCl in here, so when we put this molten Cl in here, and then test its conductivity again, you know what? It will glow. The light bulb will glow again. So when we pour the molten liquid in here, assuming that it doesn't melt the container, the light bulb will glow. Okay, so can you draw a glowing light bulb here like that? Because yes.
Will the molten turn back into solid?
Yes, as soon as you remove the heat. Yeah, so therefore you need to keep heating it to keep it in the molten state. Yes, we need to keep heating it, which is why this container has to be also a ceramic container. If it is a beaker, it will melt. Okay, and what is the other way, an easier way that we can do to turn it into a conductive substance? Yeah, is to let me draw something in here first. Yeah, is to add water. So you have solid NaCl in here again. We start from the same spot. But then, unlike in here, okay, we do not put the NaCl into a ceramic container this time. We put it into a beaker of water. We are trying to dissolve the salt. Okay, so this is beaker of water. So what happens next is when you pour the salt, NaCl solid, into water, you will get something called NaClAQ. So write down the new state symbol. So we call these things written besides the formula state symbol. There are 4 state symbols that you will encounter in chemistry. So I'll put them on the side here first. So let me put down state symbols in chemistry. We don't write the word solid, S-O-L-I-D. It's too lengthy to write. So instead, we write state symbols to indicate the state of substance in chemistry. So we write these symbols to indicate the state of chemicals, okay, in equations. There are 4 state symbols that I want you all to familiarize yourself with, okay. They are, number 1, bracket S. So bracket S means solid. Bracket L means liquid. Bracket G, as you may have guessed, means gas. And finally, we have bracket H, means aqueous. Okay, so aqueous is a solution. So put down some examples of substances that are solid. So solid include most metals, except which metal?
Mercury.
Mercury. Yes. Okay. So solid include most metals, except mercury. Just think about it. Gold. Gold is a solid, right? At room temperature. Sodium is a solid at room temperature. So most metals except Hg. So Hg is the symbol for mercury. What about some liquid substances? Well, there are 2 liquid elements, okay, at room temperature. They are bromine and mercury. So bromine and mercury are 2 liquid elements. They are liquid compounds, okay, like water. So water is a liquid compound, okay. So we use state symbols. And then what about gas? Can you name 2 gases present in the air? Nitrogen, oxygen. Okay, yeah. These are just examples. It's not exhaustive a list. Okay, don't think that, oh, I only said nitrogen, oxygen, I guess. No. There are other gases. I'm not going to write a 1,000 item that's in here. Okay, to include all of them. So just put down hydrogen, oxygen, nitrogen. Okay, so these are some examples of gases. Okay, usually things ending in gen, they are gas. Usually. Okay, bromine, is an example of halogen, but yet this is a liquid. So aqueous substances are formed when something dissolves in water. So you can dissolve salt in water to form NaClAQ. You can also dissolve sugar in water to form. Does anyone remember the formula of glucose? The formula of carbon dioxide is CO2. What about the formula of glucose you learned in biology? C6H12O6. What about table sugar then? Table sugar has the formula C12H22O11. Okay, so this, when you add water to it, it will turn into an aqueous substance. So you have sugar. So this is the formula of table sugar or sucrose. Okay, so table sugar. So table salt is just the name we give to salt. So the proper name should be sodium chloride. Same as here. Table sugar is just what we use in everyday life conversation, but the real name is sucrose. So sucrose. So this is sucrose. S-U-C-R-O-S. This is the real name. And the real name of table salt is sodium chloride. Okay? So you see, I'm just adding the state symbol AQ on the back, and then there will be aqueous solution. So in chemistry, we like to keep the conversation short. We don't write solid NaCl. We just write NaCl bracket S. Yeah, when we want to say that something is in liquid, we will just write Br2 bracket L, for example. Okay, just to keep the discussion simple and neat. Okay, so these are 4 state symbols that we have to know in chemistry. And then NaCl solid here. When we add it into water, it is turned into aqueous. So aqueous, sodium chloride. So aqueous, AQ means aqueous, sodium chloride. And in this solution, so this is not a glowing solution. It looks just like water because when NaCl dissolves, it forms a colorless solution. However, when you put this solution into the container in here and test its conductivity again, you will find that the light bulb will glow again. So the light bulb will glow. What does this experiment show you? It is that NaCl molten and NaCl aqueous, are they conductor or are they insulator? What does this experiment show when you compare the results you see in here with what you see on top? Are they conductor or are they insulator? They are conductor. So can you put down the important conclusion in this experiment? NaClS is a non-conductor or insulator. NaCl AQ, they are conductor. NaCl L is also a conductor. It's only NaClS that is an insulator. Is that clear? Okay? Because in this case the light bulb does not light up. So let me make it even more clear. You see when you put this in here. The light bulb does not light up when you put just NaClS. Without heating, without water, NaClS by itself is a non-conductor. So non-conductor. But when you heat up NaClS, so it becomes NaCl, or when you add water to NaClS to form NaClAQ, these substances, when you test its conductivity again, well, suddenly they conduct. They are conductor. And chemists, they want to know why, what has changed in this process, and they found the answer. Is that in NaClS, there are no mobile ions. The ions are locked in place. Okay, so there are no mobile ions. But when you have NaCl or NaClAQ, there are mobile ions. The ions are free to move around. Okay, and why is that? This is because both water and heat has the ability to break the ionic bonds. Okay, so you can maybe show this in here. Yeah, copy this pre-conclusion first. Very important conclusion. Solid ionic compounds do not conduct because they do not have any mobile ions. Put down the word ion. Don't say no ions. They will always have ions because they are ionic compounds, right? It's only that the ions are not able to move. So they are there, but they cannot move. But NaCl and NaClAQ, they have mobile ions. The ions can move around. Okay? And after you have copied this, can you write this down in here? In the NaClS, this is what it looks like. So we have drawn this diagram so many times now that you should remember it. So you have oppositely charged ions locked in a lattice. So this is what NaClS means. The ions are not able to move. Okay, so no mobile ions. They cannot move. But then when you heat it, or when you add water to it, adding heat or adding water can break the ionic bond. So heat can break ionic bonds. Think of these ions as like prisoners who are chained up together. They cannot move. But if you can break those chains, they can now walk around. Okay, so the ions are now able to freely move around. So this is why in the molten state, you see the positive and the negative ions, they are free from their chains. They can now move around. We see there is, so there are now mobile ions in both of these conditions. Other than heat, what else can break ionic bond? It's water. Water can also break ionic bonds. Okay, so if you ask me which of these is easier to do, I would say is an addition of water. You can create NaClAQ even at home. Every time you add salt into water, you are creating NaClAQ from NaClS. But in the lab, only when you have a crucible and when you have a Bunsen burner can you get NaCl. Is that clear? So do you now see why? Yeah, so this has mobile ions. Okay. So these two states, NaClH2 and NaCl, they have mobile ions. The ions they can freely move around. This is why these two states they conduct. But the original states, NaClS, why doesn't it conduct when we test its conductivity? Because the ions cannot move. Is that very clear? Okay, ions, mobile or non, affects the conductivity. Now, we look at, we're done with ionic bonding. Okay, so now we have covalent bond. Okay, don't worry, it gets easier. Okay, because once you understand these properties, you know the other type of bonding they are just variation of these properties. Okay, so let's turn over to the opposite side of the page, covalent bonding. There are two types of covalent bonded substances that I want you all to know. They are simple covalent molecules or simple molecular substances and giant covalent substances. So write down covalent bonding in here. So covalent bonding. So we say there are two types of covalent structures. Right, two types of covalent structures. So one is simple molecular substance. Right, so one is called a simple molecular substance. The other class, okay, is known as giant covalent structures. So giant covalent structures. Let me show you the difference between them. Okay, with an example. Carbon dioxide is a simple molecular substance, and diamond is a giant covalent structure. So tell me what you notice, okay, when I complete the following diagram here. So you have C, and then you have O, and then O. Just draw two of them. I don't want to punish you for to draw so many diagrams. Just draw two or three of them. This is what a CO2 molecule looks like. And in CO2, you have many of these same molecules. So remember, this is a CO2 molecule. So this is a CO2 molecule. When you look at the air that you breathe out, okay, you know we breathe out carbon dioxide all the time, right? When you look at the air that we breathe out, we see many of the same CO2 molecules. Okay? Yeah, many of the same CO2 molecules. And we call these discrete molecules. Meaning the molecules, while they look the same, they are identical to everyone, they remain separate. This is what discrete means. Okay, discrete means they remain separate. This is not bonded like by some very strong attraction to the other CO2. This CO2 is not bonded again to another CO2. Discrete, separate. If you really, yes.
Does that apply to all gases? Does that apply to all gases?
All gases. Yes. Okay. Yeah. So if you don't like the word discrete, you can write separate. It means the same thing. Okay. So separate molecules. What about diamond? Well, let me tell you, diamond is a very different story. Yes. Oh, okay, right. Yeah. So there are two types of covalent structures. So you have the first type and the second type. In no particular order. Yeah, you can also make this the first type and the second type. In no particular order. So diamond. Now pay attention how we draw diamond, because they will ask you to draw it in exam. If you don't pay attention, you're not allowed to draw this. First, you draw a carbon atom linked to 4 other carbon atoms tetrahedrally. So you all know what a tetrahedron is, right? Do you know what a tetrahedron is? No? Okay, well, from the look of your faces, you don't know what a tetrahedron is. This is a tetrahedron. It is a shape with 6 edges. These 6 edges, they are all equal in length. This shape, we call it a tetrahedron. Write down if you don't know this. This is a tetrahedron. You should have learned this in math class. Yeah, it is a shape with all 6 sides equal. So all 6 sides equal. And now, what I'm doing is, I will draw a carbon at the center, and then I'll draw 4 carbons at the edges, like this. So put a carbon in the middle. And then put another 4 carbons at the edges. We are just drawing something like this. Okay, and connect them through bonds. Like this. Okay, so connect them through bonds. So this is the tetrahedral structure. So the carbon, they are connected to 4 other carbons tetrahedrally. So you can see the tetrahedron in this structure, right? Can you see this tetrahedron in here? Yes, this is really shaped. And now, I know you can't do this, but I can, because I'm using now. And okay, you try your best to copy, you see what I'm doing? You are copying this over, like this. Then you'll be able to draw the structure of diamonds. Okay, let me show you what I did. Okay, so you just have to repeat this structure. To me, it looks like chicken leg. Does it look like chicken leg? Doesn't it look like chicken leg? It looks just like this, right? You see. So you just draw something that looks like this. Okay. Yeah. Right. So you have a structure that looks like this. Right. So this is the structure of diamond. So practice a few times, okay? And then you will be able to draw it, okay? Yeah. As they will ask you to draw this structure in the exam. I only want you to know that if this is what a tetrahedron looks like, you're just repeating tetrahedron here, here, and here. It's difficult to draw, I know, but you have to practice. Okay? So this is the structure of diamond. So what do you see? What are these forces? Yeah, so what are these forces in between the atoms called? Remember? What is the name of the bond that holds non-metal atoms together called? Is it ionic, covalent, or metallic? Covalent. Remember, if you don't go back to this part of the table, what did we put under covalent bond? We wrote formed by non-metal. So if you see 2 non-metal atoms next to one another, this is covalent bond. So you have covalent bond in here. These attractions on the right, they are also covalent bond, as they are also holding the non-metal atoms together. So these are also covalent bonds. But what is the difference between diamond and carbon dioxide? In here, this whole thing is a giant molecule. Do you see separate molecules in here? No. But in simple molecular substance, you see many, many small molecules. Okay, so that's the difference. Can you draw a very, very large? Yeah, okay. Yeah. Actually, the structure doesn't end here. When you look at a piece of diamond, there are many, many carbon molecules what you're seeing right now. We're talking about like billions, okay, or billions of carbon atoms in a small specks of diamond. So this thing, this single large thing in here is a giant molecule. Okay? So therefore, we say giant covalent structure, they usually do not contain discrete molecule. They contain single giant molecule. Okay, so single giant molecule. It's giant because this molecule doesn't just have 1 or 2 atoms, but many, uncountable. Yeah, and for simple molecular substance, I want you to write small, discrete molecules. Not only are they individually small, there are also many of them. Okay, so these 2 descriptions you need to know. Okay, so small, discrete, single, giant. Okay, so small here means, of course you know what small means, but I want to put that. It contains a countable number of atoms. When you say it's giant, okay, it means it contains an uncountable number of atoms. You won't be able to count how many carbons there are inside diamond. There are just too many. So uncountable number of atoms. Okay. underline the word uncountable. Uncountable. Okay? And in here you can count. Each CO2 molecule has 3 atoms each. But diamond, well, I lost count. I don't even want to count how many carbon atoms there. It's uncountable. So that's what sets apart simple molecular substances and giant covalent structures. So first, we will discuss the simple molecular substance. Okay, on this page. We look at some of the properties. Okay, there are many molecules that I can think of that are simple molecular substances. So write down simple molecular substances. So they may be elements or they may be compounds. So now that you have such a large blank page, you can write notes on this side. Okay. So simple molecular substance, they can be elements or compounds. Okay, so they can be elements or compounds. I want to give you a lot of examples here, okay, so you can see. So they can be elements like O2, H2, N2. Okay, so they only differ in the way they are bonded. For example, O2 means there is a double bond. So we already saw why O2 will form double bond. Do you remember? Why would oxygen form double bond? Do you all remember? That's because with a single bond, make them stable, make them happy? No. Okay, if you're unsure, let me go back here first real quick. Do you remember oxygen? We discussed it here. When you force oxygen to form single bond, are they happy? Are they satisfied? No. They are only satisfied when they form two pairs, when they share two pairs of electrons, aka a double bond. Which is why, you see everything is connected. Which is why I draw two lines here. We don't draw a random number of lines in between atoms. So this is what O2 look like. Okay, and what about H2? How many bonds do hydrogen need to form to satisfy themselves? Only one. So this is why we draw only one line here. And finally, for nitrogen, can you draw 3 lines? I want you to think about this tonight. Why would nitrogen form a triple bond? Show me the explanation in the next lesson. Okay? And remember to bring this worksheet back. Okay? Yeah. So these are the elements. Okay, we will continue the discussion next time on compounds. So you can put down some placeholder here. So for compounds, we have some examples. You can put down the placeholder here. Okay?